Okay, so let's start off here, part 1 of homework 8-5 with question 1. Question 1 asks us if we want to double the rate of energy transfer. Right, so if I want to double that rate of energy transfer, well, the easiest way to double the rate of energy transfer is to double the energy. And the energy of a wave is 1/2 Ka squared, right, or 1/2 Kx squared, where x is the amplitude. So if I want to double the amount of energy carried in a wave, I need to do something to double this quantity. So if I look at the options, well, if I increase the amplitude by a factor of 8, that's actually going to make this way too big, right? That would be 64 times bigger. That's not going to work. 4 times is still too big. Doubling it is still going to be 4 times as big. So the correct answer here is we're going to increase it by a factor of radical 2. That way when we end up squaring the amplitude, we actually get 2 times, right, 2a squared. So that would double the energy for us. Question 2 is a pretty good question for making sure we realize the difference between these two terms, right? So the intensity level is talking about the loudness in decibels, whereas the sound intensity is talking about our intensity in watts per meter squared, right? So if I look at option A, they ask which of the following is true. If I look at option A is not true because the sound intensity cannot be negative. We either have a certain amount of power or we don't, right? So the sound intensity cannot be negative. So that's false right there, and therefore that option is not true. The intensity level in decibels obeys an inverse square law, but the sound intensity does not. Well, we know that the sound intensity, in fact, does obey inverse square law, right? If I look at this again, it's the sound intensity equals watts over meter squared. So as the distance gets bigger, the intensity decreases, which is definition of the inverse square distance there, right? So that is also not true. Both intensity level in decibels and sound intensity obey inverse square laws. That is not true. The intensity level in decibels is a logarithmic function, right? It is not based on the inverse square law. It does not directly or inversely relate to the intensity. So that one's not true. And then option D actually is the correct option here. The sound intensity can never be negative. The sound intensity can't be negative. We just said it can either be 0 or a positive number, but the intensity level in decibels can be negative. And that's true. If we had an intensity that was below the threshold of human hearing, right? So if you had, for example, like log of 1 times 10 to the negative 13th divided by 1 times 10 to the negative 12th, this would be less than 1. Then this logarithmic function would be a negative value, making that sound level, that intensity level, negative. So that is a true statement, right? And then both cannot be negative because we've already said the sound intensity can't be. Right? So option D is the correct option for question 2. Okay, so this question is a good question just to make sure we're kind of comfortable with the algebraic representations. So they give us the velocities here. They tell us it's the same speed. One situation is a plane flying towards the stationary siren, and then the other situation is the siren moving towards the plane. And they ask us if it will be the same frequency. And your gut might say yes, it's going to be true, right? Because in either case, they're moving towards each other, right? So either here's the plane moving towards the sound source, or here's the sound source moving towards the plane. Right? And so in either case, we might be thinking it's going to be the same frequency. That actually doesn't end up being the case. If we look at the algebra behind it, the frequency for when the source is moving is the denominator, right? So this would be my representation for when the source is moving. However, the frequency for when the observer is moving is messing with the numerator, right? So this is my representation here. So in one case, I'd have something like the speed of sound, which is 343 over 343 plus 1/4, right, that speed. So we'd have something like that. And then in the other case over here, we'd have 343 plus 1/4 343 divided by, in this case, it'd be just 343 on bottom, right? And so, in fact, we can see by looking at this, and excuse me, this wouldn't be addition on bottom, this actually would be subtraction. That makes more sense since it's moving away. Or moving towards. But anyway, if we were to look at this though, what we actually see is these are not the same fraction. These are not the same ratio. 343 divided by this difference is not the same thing as that sum divided by 343. They end up being a different ratio. And so because we're taking each of those ratios times the same frequency, we end up getting a different perceived frequency for either case. Right? So the algebra behind this basically is saying that 6/5 is not the same as 5/4, right? That's an exaggerated version of this question, but that's more or less what this question is saying. So anyway, make sure it is something you're comfortable with here, right? That depending on whether the source or the observer moves does make a difference, right? So it is going to be false. They are not going to perceive the same frequency. Okay, so for question 4 here, a stationary siren, very similar to what we just looked at for question 3, emits a sound with a frequency of 1000 Hz and a wavelength of this. An observer who is moving towards the siren will measure a frequency and wavelength for the sound such that, and so this is just getting kind of to the core nature of what happens with the Doppler effect. Well, first and foremost, hopefully we can rule out D, right? We know that if we're moving towards the sound source, the frequency is definitely going to go up. So the frequency is going to increase. So then the only tricky part is what happens to the wavelength, and the answer to that is nothing, right? Nothing happens to the wavelength. The reason that we perceive the frequency to be higher is because as the source moves towards, so as the observer moves towards the source, I should say, the relative velocity between them, right, the new velocity between them, becomes the sum of those two speeds, right? So this is the new velocity that I'm working with. The wavelength doesn't actually change, the velocity does. And as the velocity changes, right, if the velocity changes and the wavelength doesn't, then we perceive a new higher frequency. Right, so option B is my best option for question 4. The wavelength does not actually change, but the frequency does. Okay, so question 5 here is a good one for the wave velocity on a string. Right, so you've got a string suspended there, it's hanging from the ceiling, and then at the bottom of the string you have a stone. And so the context here says you've got that string, and they give you the mass and the length, and that always should jump out to me as, hey, they're giving me the mass and the length of the string, so now I know my linear density, my mu, right, which would be 0.00825 kilograms divided by the length of 0.65, right? So I've got that measurement if I need it, which we in fact will in a little bit here, right? But the idea of what's going on is, so you pluck the string and send a pulse down the wave, right? So you send this disruption, this disturbance down the wave, and then it returns back after 7.84 milliseconds, right? And so what does that information tell us? Well, that tells us how fast the wave moves down and back, and so they're giving us a velocity, right? They're giving us a means to find the velocity. We can find the speed of the wave by finding that total distance divided by that total time, right? Since the wave velocity is going to be constant, we're just going to find the total distance divided by the total time. So the total distance would be 2 times 0.65, right? Because it has to go down and back. And then the time is again 0.00784 seconds, since it is 7.84 milliseconds. And so that tells me then that the velocity of the wave is about 165.8 meters per second. So obviously rounding that off to a few places there, but 165.8 meters per second. So that's how fast the wave is traveling. So then they ask us, how heavy is the stone? Well, to find out how heavy the stone is, right, I know that the stone is going to be pulling down with the force of gravity. If I could find that force of gravity, I could easily just divide by 9.8 to find the mass of the stone, right? So how does force of gravity relate to this question? Well, the force of gravity is going to be equal and opposite to the tension in the string, right? And so that's what's going to tie all of this together, right? So the velocity equals the square root of tension divided by mass per length. And then since I now know the velocity and the mass per length, I can find the tension. And once I find the tension, I can find my mass for the stone, right? So the velocity again of 165.8 equals the square root of, I don't know the tension, but I do know the mass per length, 0.00825 divided by 0.65. So at this point, it's just a matter of solving this equation for tension, right? So I do a little bit of arithmetic there. I get the tension to be about 348.98, so about 349 newtons, right? That's my tension. And then don't forget, we're looking for the mass of the stone. And since I know that the tension equals the force of gravity, I know then that the mass of the stone would just equal the tension divided by 9.8, right? Since this is mass times gravity, this would be tension divided by 9.8. So my mass equals 349 divided by 9.8, which is about 35.6 kilograms. Right, so a very good question for tying in the velocity on a string with an equilibrium type problem, right, where we have to set up tension and force of gravity. So definitely a good problem to make sure you're comfortable with. If you do have any further questions, just let me know so I can help clarify that question a little bit more. Okay, so question 6, hopefully a pretty easy question here. Just gets to kind of the proportionality of intensity, right? So we know that if I'm looking for comparing the intensity between two locations, then that is inversely proportional to the square of their distances. So RB squared divided by RA squared, right? This is the relationship I want to set up. As soon as I set this relationship up, it's a pretty easy plug and chug type question, right? So 1.1 times 10 to the negative 7th is my initial intensity at location A. I'm looking for my intensity at 4 meters away, right? So anyway, so I'm 3 meters away then at location A, so 3 squared goes on bottom, and then 4 squared goes on top, and then just solving again from here to find out my intensity for B. Now, always let intuition help you out a little bit here. We know the further away we get, the smaller the intensity should get, right? So if this number were to get bigger than 10 to the negative 7th, if this was be like 10 to the negative 6th, that would be an issue. But in fact, if we solve this correctly, this should be about 6.19. So about 6.19 times 10 to the negative 8th. And then my units again, watts per meter squared. So anyway, I've got this question hopefully solved without too much trouble. Again, just let intuition help you out a little bit. The trickiest part is to remember when is it squared and when is it not squared. This question is definitely a good question for kind of opening it up a little bit more. It's not quite as just straightforward plug and chug. There are a few more tricks to make sure you're paying attention to. So part A asks us what is the intensity of the waves at both 2.5 meters from the source and 10 meters from the source. Well, to find it at 2.5 meters, they actually give us a lot of information there, right? And so let's just boil this down to the definition of intensity. So I'm going to call 2.5 meters my location A. The intensity at location A would be the power divided by the area, right? Now, we don't know the entire power, we don't know the entire area, or at least we could calculate it, but we don't know it right now. But we don't actually need it for the very first part here, right? In fact, all I need to do is, since they give me this much area on the sphere that receives that much energy, right, or the rate of energy, which is joules per second, which is a secret way of them giving us the power, right? Joules per second is watts, so that actually is a measurement of power and not energy. So they're giving me how much power that much area receives, and that is the intensity, right? That is what the intensity is by definition. So the power of 4.2 joules per second is given to an area of 3.25 centimeters squared, and I do need to make sure I pay attention to centimeters squared, right? That is actually then 10 to the negative 4th meters, because I'm dividing by 100 twice since it's centimeters squared, right? Centimeters squared, I divide by 100 twice to convert that to meters. So anyway, make sure we're comfortable with that part. But once I establish that fact, that again gives me the intensity for that entire location, right? So even though it's just a part of the sphere, so if I was drawing kind of the sphere, even though it's just a little square on that sphere that's receiving this much area, intensity is a rate. It's a ratio between power and area. So the intensity for that square is going to be the same as the intensity all throughout that sphere, right? It's just a proportional relationship. So I've got the intensity then for part A. I just need to calculate that, and that ends up being about 12,923 watts per meter squared. So that's my first intensity at location A. So then to find the intensity at this second location, 10 meters away, now I can do exactly like I just did in the last question, in question 6, right? And I can set up my proportion. So I can set up my proportion to look something like this. And now that I know both distances are 10 squared and 2.5 squared respectively, and I know my intensity at location A, it's a pretty easy plug and chug to solve for my intensity at location B, which ends up being about 808 watts per meter squared. Right? So I've got those two measurements without too much trouble. So hopefully part A wasn't too bad. Part B here is where it does get a little bit trickier. So for part B, they ask us, at what rate is energy leaving the vibrating source of the waves? Well, again, they're asking us for what is the energy, or what is the rate, excuse me, of energy leaving the source. So when they ask for the rate of energy, keep in mind they're really asking us for what power, right? So they're asking us how much power leaves the source at a certain time. Well, the key concept here is that power is not created or destroyed as the wave travels, right? What happens to that power? Well, the power just simply spreads out over a larger and larger sphere, right, over time. But the total power is always constant. So if I want to find the total power, I just need to find the intensity at a certain location, which I already know, and I need to find the total area of the sphere at a certain location, which I can do. Right? So if I want to find the total power, I just need to find the total area, the total surface area. Since I know the intensity at location A is 12,923, I want to find the total power. The total area for the sphere would be 4 pi r squared. So I just need to solve that at 2.5 meters away, and when I do that, I'll leave it to you to do that. And when you do, you should get about 1,015,000 watts of power from the source.